Hey guys, welcome back. I was gonna post the videos from class today, but I realized that I had the wrong settings, so people's faces were in there. So I don't want, again, to protect your privacy, and also because the resolution was bad because of that. I'm just recording all the questions from today's class. So if you missed it, don't worry. If you missed the class, don't worry because this is gonna be the same stuff anyways. You can just watch it here. I am gonna change one small thing though. Actually, no, I take that back. I'm gonna approach it pretty much the same way as in class. Let's start by looking at the change of base formula. This is 4.3 part 2. We're looking at essentially the change of base formula. That's the big thing for the whole lesson. And then we're gonna apply that to calculate logarithms using a calculator. Let's start with what the change of base formula says. This is on the first page, the first box. Now it starts with these stipulations on what A and B can be. A and B are the bases. So that A and B be strictly greater than 0, and A and B not equal to 1. And then it says that M be strictly greater than 0. So with that set up in mind, then we have this. This is the change of base formula. Also, you can think of it as a change of base theorem. It says that a log of base A of M is the same thing as log base anything. And in particular, you can choose it to be this B, but any B is fine, of M over log base, same base B of A. The way I remember which one goes on top and bottom is the lower one goes in the denominator, upper one goes in the numerator. Yeah, higher one and lower one. The base goes in the basement, kind of. And this log base B could be any log. So what I like to also think typically is you could replace that with the log base E or ln of M over ln of A. Again, but this could be any base. So you could do the common log if you want to, just regular log base 10 of M over log base 10 of A. And you can choose, you can take your pick, whatever you want. It's going to work regardless. Okay, so that's the statement of the theorem. I do want to come back to, though, what about these stipulations? Why does A and B have to be bigger than 0? Well, actually, remember before with me, if it's 0 or less, we actually have an issue, right? Because what's log base of a negative number? Here, what's log base of? Oh, well, let's look at what's log base of 0 as an example. 0 to what power is equal to M? Well, in general, it's not going to have a solution, right? 0 to what is equal to M? Unless M itself is 0, then there's no way to get that. And in fact, if M is 0, then we say it's undefined because what's log base anything of 0? That's why M has to be 0, because what's log base A of 0? A to what power is equal to 0? Well, it doesn't matter what A, there's nothing that's going to give me exactly equal to 0, no matter what power I take. So this is actually undefined. And similarly, it's undefined for negative numbers, right? Yeah, also undefined for negative numbers. So log, it has a domain of positive numbers. It has to be bigger than 0. That's why this M has to be bigger than 0. These other guys also have to be bigger than 0, or else I run into issues like this, right? 0 to what power is equal to M? Negative number to what power is equal to M? Same thing. That's just a quick note about those stipulations that you have. All right, so the gist of the formula, though, just comes down to this part right here. No matter what base I have of M, I can replace that with any base I want to, any base of my choosing, top number over bottom number, top number over bottom number. So let's see if we can apply this to Julian questions number 1 through 5. And then at that point, we're going to come back and look at why the theorem is true. Because in the question in the class, we had a good question about why it's true. And I think it's worth looking at the proof of it. But I'm going to kind of follow an unorthodox approach here. We're going to do some problems first, and then come back to the proof for why it's true, because I think it helps to just kind of get some practice under your belt and see it in action. And then we'll come back to seeing the justification for the thing that we've been using. Okay, so let's let's do a couple of questions first. Number one, start with number one. We're looking at log base 3 of 10. We want to write that in terms of ln. And number two, almost the same question, log base 3 of 10 again. We're going to write that in terms of logs, or the common log, meaning log base 10. Let's do 3 as well. We're going to rewrite log base x of z in terms of ln. Okay, so first one first. Change the base formula says I can replace that log base 3 with any base I want. So in particular with ln, on top and bottom. And top number goes on top, bottom number goes to bottom. This is log base e of 10 over log base e of 3. That's it. That's the answer. Number two, same principle. So if I'm going to use the common log this time, so log 10, log base 10 of 10 over log base 10 of 3. That's it. Top number over bottom number, top number over bottom number. That's your answer. So actually, all three of these things, there you go. Log base 3 of 10 is equal to log ln 10 over ln 3, which is also equal to log 10 over log 3. Okay, number 3 now. So we're writing this in terms of ln. That's ln of the top number z over ln of the bottom number x. That's it, done. So those are the first 3. Okay, let's look at 4 and 5 now. We'll look at these one at a time. And now I'll remind you of the old way we used to solve this, because you actually have 2 options how to solve these guys, or evaluate them, I should say. Number 4, evaluate log base 8 of 16. Okay, so right now we're using the change of base formula to solve this, but let me remind us how we used to solve this. And I'll show you it's a little bit longer, but when you come across a question like this, you actually have an option how you want to approach it. So let me just rewrite the same question twice. Old way was to look at it definitionally. By definition, that says 8 to some value y is equal to 16, right? And you're trying to figure out what is this y. That's the definition of a log function, right? Okay, well, to solve this, it's not clear right off the bat, because 8 to the second power is already 64. That's too big. So y, it turns out to be some kind of fraction to get to where I want to go 16, right? Well, the way I can do this is, remember, we write it as the same base. I can write 8 as 2 to the third power raised to the y power, and 16 I can write as 2 to the fourth power. So now I have them in the same base, right? This I can rewrite as 2 to the 3y is equal to 2 to the fourth. And then now that I have the same, that looks like the 24, sorry. This is 2 to the fourth. Now that I have the same base on both sides, I can just solve for their exponents. Right? So I do 3y is equal to 4. That means y is equal to 4/3. And there it is. That's the answer. That's the evaluation of my log base 8 of 16. All right, let's try the same question using what we just learned, the change of base theorem. I can rewrite this now as, instead of using log base 8, I'm going to rewrite using log base 2, because 2 to the third is 8 and 2 to the fourth is 16. Both of these values, there are powers of 2, right? So I can write this as log base 2 of, remember, top number on the top, and log base 2 of bottom number on the bottom. It's 2 of 8. What's log base 2 of 16? Well, 2 to the fourth is 16, so that's 4. And what's log base 2 of 8? Well, 2 to the third is 8, so that's 3. And you see I get my answer in basically 2 steps. 1, 2. This one took a little more work, but same answer in the end. So either way, it's actually okay. All right, we're going to do the same thing for number 5, and then we're going to take a small break. Or, well, I'm going to take a break. You guys will just continue to the next video, I guess. You can take a break if you want to. Okay, number 5. The question is log base 1/3 of 9. All right, let's look at the old way too again. Start with the old way, in fact. This is saying, by definition, 1/3 to some value y is equal to 9, and I want to solve for that y. Okay, well, first thing I notice is I've got 3's. This is 1/3 is really just 3 to the negative 1 power. And 9 is really just 3 to the second power. So basically I have the same base now. I can rewrite this as 3 to the negative y is equal to 3 to the second. And again, I'm going to look at my exponents. Negative y is equal to 2 means y is equal to negative 2. There's your answer. Or this is the evaluation here, the negative 2 part. Okay, the new way, using change base. I'm gonna again use base 3, top number on the top, and bottom number on the bottom. Well, log base 3 of 9, 3 to the second power is 9, and log base 3 of 1/3, 3 to the negative 1 power is 1/3, because it's in the bottom side. It's 1 over 3, so it's negative for that reason because it's in the denominator. And 3 to the 1 is 3, so it's a 1, negative 1. And of course, 2 over negative 1 is of course just negative 2. So here we see the answers match up again. That's it. Okay. So break time.